Let's discuss about gradient descent in this today's session. In the previous sessions, we have already looked at what is a linear regression and what is a logistic regression. And we discussed a point wherein we have used some kind of a loss function to gauge how bad the model is performing. And we use that loss function to update our beta naught and beta 1 values in order to reduce that loss function and give a better model. So we are going to discuss more about that loss function and how are we arriving at better beta naught and beta 1 values using that something called as a gradient descent. All right, so before I move forward, let us say that we have some kind of hell like this, okay? And imagine that you can be at any peak that you want in this mountain, and the agenda is to find out a horizontal space wherein you can put up your tent and rest for a while. So given such scenario wherein I ask you to imagine, maybe like, say, depending upon the number of peoples, anyone could have imagined anywhere. Let us say that I have imagined a place that I'm going to start somewhere here. In order for me to find out a place where I can put up a tent, I need to find something which is horizontal. And when do I know that I have reached a point that it is horizontal? So I take one step at a time and I keep moving downwards from here. So the change in altitude tells me that I'm going down, and the change in horizontal position tells me number of trials that I have made. So I can convert both of these to repeated number of times and find a point where I can, let us say that this is the area where I can put up a tent. Okay, so in order to do that, I need to do two things. I just need to keep out moving downwards, and the second thing is I need to find out if I have reached a point where it is horizontal. Okay, so this is what we are going to do. This, whatever uneven surface that you're going to see, is nothing but our loss function. This would be our loss function J that we discussed in logistic regression class, and this is nothing but the local minima. Why I say it's a local minima is because you could put up a tent here, or maybe you could put up a tent here, but because you have already reached a horizontal space in this particular region, probably you would end at this point. But given a case that I have started off from this one, then maybe I would have reached this one. So you never know where the starting point would have been. So just keep that in mind that when we start making iterations, our our intention is to find out how to reach to the local minima, if not the global minima, at least to the local minima. So far, so good. So what next? How to identify that we have reached this horizontal space, and what is the steps that we are talking about? So let's move a couple of steps back and see what mathematics say. Let us say that we have some kind of a function which is like this, okay? And I randomly pick two data points on this particular function. When I try to make a line through it, if I find any curve below the line, then that line or the function would be called as a convex function. If the curve is above the line, then it would be a concave function. Given that our loss function is convex, why I say convex is that you're able to find out some kind of a lowest place or lowest combination of betas where the model is performing very well, or the loss function is too less. So our model tries to go in the convex function route. So we have some kind of a convex function, and when I say we have a convex function, it means that we definitely have some kind of a point where the loss is completely negligible. So this point where you call the loss is completely negligible is called as a gradient point. And the gradient at this particular point, the gradient is lost, or it becomes zero. At least in the mathematical point of view, it becomes zero. So if at all we have to reach to this particular point where we have the gradient as zero, we have to find out the slope for each change of x. So for example, if I have started at this point and I started at this point, and as I see that when I draw a line, I find that the slope is some value. I move little steps forward. Now I draw a line here and see what is my slope. I move steps forward. On doing so, when I reach to a point where the horizontal line is, I mean, the tangent is almost parallel to my x-axis, it would mean that the gradient has almost vanished, or it is very close to zero. So what we can do is, like, we can take one simple convex function and understand what I was saying here. Let us say that I start off with one simple convex function like this, x square minus 5x plus 10. And if I plot the values of x and y, this is how it looks. Okay, it is completely like a convex. And as I said, like, if you draw any line where it crosses two data points of this on this curve, then you can find that the curve is below that line, so it is a convex function. And what we are trying to do here is, like, we have to find out a point where this minimum occurs. In order to do so, what we have to find out is, for a given change of x, the change in loss function should be zero. That is what we are trying to find out. If I make any changes to my x, say in the case of mountain, I'm trying to move in one direction, but the altitude is not changing. So it means that I have reached to a point where the gradient has lost. So in order to find such a point, I have to make this particular equation calculate its first differential and see the point where the first differential becomes zero. So if I calculate the first differential for this equation, it would become 2 times the x minus 5. The point where 2x minus 5 becomes 0 is our minimum point. And as you can notice, like, when x is 2.5, then the gradient would become 0. So at this point, so mathematically we can do that. So we have to just find out the first differential of our equation, and using the first differential, wherever the first differential is becoming 0, that is a point where the the function is having the lowest value. Okay, so given such a case where we have some kind of a loss function which is denoted by j, and we have multiple values, like, let's say this is x1, this is x2. So we have to find out proper values of x1 and x2 such that the loss function is very less. So in order to do that, what we will be doing is, we will be taking two things. Like, we will be doing couple of things like learning rate. We are trying to understand which direction I have to move, and what is the change to beta that I have to make in order to get this loss function to the lowest possible. Okay, so the stars that you find, one star to another star, is nothing but the step size, or the learning rate. Okay, using that learning rate, I'm trying to change my value from this star to this star. I'll explain that in a detailed way. So we have to identify, we know that there is something called as minima for a given convex function, and our agenda is to find where that minima is. In order to find, we should also be knowing in which direction I have to move. So I cannot move just around any direction, right? I have to move to a proper direction where that local minima is present. So in order to do that, we just have to find out two things about. One is the learning rate, how fast I want to update my weights, and how many times I have to update my weight. Okay, so the how fast you want to update the weights is nothing but the learning rate. So I'll show you one simple Python use case wherein we can discuss about this learning rate. And step size is nothing but how many times you want to update. Say, in order to reach a local minima, I want to try like 100 times. If I'm unable to find the minima in 100 times, it means that I cannot find it even if I repeat 1,000 times. It's just waste of time. And how would I update my weight? Say, for example, my previous weight was wi. The previous weight was wi minus 1. what I would be doing is I would be simply subtracting the learning rate and the differential of my loss function. The differential of the loss function is denoted by this delta J. Okay. Even if you do not understand anything, don't worry about that. We are just going to look at how the we do this in Python use case. Let me just open the Python notebook and show you 1 minute. So let us say that we take simple functions. For doing that, let me take the necessary libraries as NumPy, and I would like also to show you some plots. Okay, and I define some simple function. Let us say my function is lambda. I can also write a one-line function like this. Say my PDA input would be x, and the equation would be x to the power of 2 minus 5 times of x plus 10. I think this is the function that we have taken. 1 minute. Yep, I think we have taken the same function, x square minus 5x plus 10. So what I'll be doing is I'll be continuing with that only, x square minus 5x plus 10. And now what we'll be doing is, let us say I want to pass some variable to it. So I'll say function of 1. So I can get the value of 6. Or let us say if I want to say function of minus 1, I can get the value of 16. Now what we'll do is we'll try to differentiate, find the first differential. Now first differential, I'll just try to hard code it. Is equal to 2 times, sorry, lambda of x, and this would be 2 times of x minus 5. I hope you understand what the differential means. Whatever we have in the numerator, in the power, right? We will get it. We normalize it. It will become 2 to the power 2 times x, and the change of 5x would become only 5 because x will be lost in the differential. Okay, so we would have an equation like 2 times x minus 5. This is the first differential equation. And just like that, if you want to find out for a given x, what is the value? Say for example, for 1, my value is minus 3. Okay, we have two equations. Now this is my actual loss function. This is my actual loss function, and this is a differential of my loss function. Let me write the comment. And this would be first differential of our loss function. Good. Now, what we need in order to form like a curve like this, we need different values of x so that the y can be calculated. Now, in order to do that, what I'll do is I can use np.linspace and get all the values. Say I define x is equal to np.linspace. I say that my values should range from minus 10 to plus 10, and I need about 400 values. And just because I have x now, I can just show you x, let us say the first 5 values. You can see the first values are like this: minus 10, minus 9.94, 9.899, and it's an increasing order. Okay. Similarly, if you want to find y, I simply have to substitute in our function. Our function name is func, and we'll put value of x. Just like that, we can also find out first 5 values of y, and we get some array. Okay. Now what we're going to do is we'll define our gradient. Now for gradient purpose, we define our learning rate. Let us say the learning rate is 0.1, and I say I was mentioning that we will be randomly starting at one point over the top of the hill. Say I start my first value at 9. Okay, and there is something called as, let me show you. So all the changes that I made to my values of x, I'm going to store it in something called as steps. So first my initial start would be, sorry, my initial step would be x start. Okay, and then I want to make number of iterations, how many times I want to update. Let us say I want to update for 50 times. Okay, these are the values that we are going to take. Now what we'll do is we'll try to make this iterative. Like I want to run this program for 50 times. What I want to do is every time I find out the differential, I want to multiply with learning rate and update my weight. So how we'll do is, say for underscore in range of number of iterations, I would say x of start is going to be updated by x of start of previous value minus learning rate into, we want to take the differential function here, differential function of x underscore start. So whatever is our previous value of x start, let us say if I start from 9 minus learning rate into function difference of 9, that will be my new weight. Okay, and then I will also append it to steps just to plot it in a proper way. Append x underscore start. Okay, this would be quick. It's just 50 iterations, so it should not take much time. Now let us see how we can plot it. Okay, now I'll just take figure and fig size equal to, let us say 10/6. I'm going to say plt dot plot. First we'll plot only x and y, and I want the line width to be like 2, and then I'll plot my, say, scatter plot. I'll say I want to plot all my steps followed by function of np dot array of steps. I'm getting all my y. In scatter plot, we need to define what is our x and y. So I'm just showing what is my x and what is my y. Once the y is completed, then I can say I want to denote them with red dots, and the size of the dot should be 100 pixels, and label should be steps. Okay. Once the scatter plot is over, we can also plot just x and y. Plt dot plot. Again, I can say steps followed by function of steps, and then color equal to, maybe, let's see if I can keep it for red now, and line style start is equal to this, and line width is 1.5. I can add some titles to that. plt dot title, say this is gradient descent, and I can add x labels. This is my x. plt dot y label is my function of x, and I also want to show the legend. Maybe grid works first, show, and then plt dot show. When I do that, you can notice, right? So we have started off randomly at 9. Let's say this is this is the x equal to 9. we have started here, and you can see gradually the weight is getting updated, and we are trying to reach to a point where we have reached this, where x is equal to 2.5, the point where the loss function is vanished or equal to 0. Now imagine the same function I'm going to take and I'm going to change it differently. Like, okay, let us say instead of making as x square, I'll make it as x cube. Okay, and then I'm going to repeat the same thing. I'm going to take the first function. The first differential would become 3 times x minus 5. Function difference would be that lean space again, y, learning rate would remain same, and then I'm going to plot it one more time and see what happens. Now this is something called a saddle point. Okay, now what I mean to say by saddle point is our gradient descent thinks that this is the local minima, but the curve is still going down. Probably the local minima is somewhere down below. Okay, but our iterations are stopped because we have kept a limit of 50 iterations, and we saw that for finding us the minimum, we just have to find a point where uh, change in gradient should be 0, or the gradient should vanish. So it has reached to a point where the gradient has vanished. But the gradient can vanish at multiple places. It can vanish at a local minima or a global minima. Okay. So in order to avoid having problems like a saddle point, we need to randomize our records, or we need to make sure that uh, you try out with different set of values. Of course, we are not at a point where we already know deep learning. Okay, we did not discuss about deep learning, but if you already know deep learning, there is something called as randomization of weights, where you start with uniform distributed weights, so that this kind of a bottleneck doesn't happen, where you don't get logged at a local minimum, which is not good for our model. Okay, I think I made it pretty clear about gradient descent. I will be happy to help if you have any doubts. Thank you.